Good morning. Welcome to Control Systems Seminar and Webinar. The last sessions we saw some of the control systems mathematical analysis related to Laplace transform. We saw a simple example which explained to us what was Laplace transform and what was it about. And we also saw some examples which required the inverse Laplace transform to convert the polynomial partial fractions into the E curves, that is exponential curves. This was not enough for us to analyze the control systems entirely. The control system has got many analysis like root locus design, Nyquist plot, and polynomial analysis, and board plot, then complex plane analysis, etc. However, all these involve the Laplace transformation, and also even the plots require some values in terms of the xy plane. So we will see now a simple example related to the Laplace transform. I have worked out some of the numerical examples which is very essential for indicating how the Laplace inverse transform and the polynomial equation are being very valid for the control system analysis. We get a control system transfer function in terms of polynomials where we represent the polynomial as a numerical function with a numerator and denominator. The numerator resolution has got zeros and denominator resolution has got poles. So we can say that it is zeros by poles instead of numerator and denominator. And now we want to see the numerical polynomial in terms of the transfer function and in terms of the partial fraction. If we split the numerical term in the partial fraction, we get some values which are very essential for us in individually attending such a fraction with the inverse Laplace transform, so that we get the sum up or negation of exponential curves. This negation of exponential curves lead to series. This series can be converted into a sine or cosine, or it can be converted into a plot in a xy plane. This is what we want about the control system. This is how the instrument in the control system processes. Now we will see the simple example of the polynomial which I have worked out now. Shown is the polynomial which says it is a 3s plus 1 by s minus 1 into s minus 2 into s plus 1, which is resolved into partial fraction. Partial fraction as shown. This partial fraction, you can see that it has got three constants, a, b, c. These three constants have to be found out by some method. First, I am going to equate the numerator with this partial fraction such that I multiply the denominator of that particular polynomial with the partial fraction obtained, and then I equate particular s value such that I negate the two terms with a constant, that is b and c are negated, but I have a a. With the a, I am going to substitute the value and I get a equal to minus 2. Similar way, I can find out the values of the b and c such that this b and c are substituted in the partial fraction, and then I am getting a function like minus 2 by s minus 1 plus 2.5 by s minus 2 and minus 0.3 by s plus 1. This is going to yield us my partial fraction which can have an inverse Laplace transformation. When I have the inverse Laplace transformation, I can retrieve the curves which are added exponentials, or they may be a negative exponential as you have seen here. So this concludes that Laplace transform or inverse Laplace transform is a good method for analyzing these polynomials. Polynomials are obtained as a very complicated equation from the transfer function of the control system. The transfer function of the control system is generating the polynomial. We cannot have the polynomial representing any other system, but it is going to represent only the transfer function of the system. There is no other go. So if we know the input of the particular system, suppose the impulse, this is going to be multiplied by the transfer function of the system, so that we get the output. For example, y of t equal to x of t into the particular h of t, but we cannot relate this in a time domain response, so we are converting into a domain. That means y of s equal to h of s into x of s. So the input signal is also represented in the S domain. the transfer function is represented in the S domain and the output signal is represented in the S domain. That means we are manipulating the transfer function of the system as a polynomial, and it is going to get multiplied or somewhat divided by the particular signal, incoming signal, so that the incoming signal gets modified into output signal in the S domain. Then if we convert the S domain into the time domain back by the inverse Laplace transform, then we get the original signal which is manipulated in the output by the control system. This is how the instrument processes the control system input signals. So it is a very good example showing how we have manipulated successfully particular input signal with the control system transformation method. And this is the outline of a simple transfer function which has got zeros and poles, but the transfer function with the zeros and poles is complicated in circuit level. In circuit level, such a transfer function cannot be analyzed, but in the polynomial level, it can say that this particular block has modified the input signal to a great extent that our output is going to be in relation to these exponential curves represented as an addition. So I want to lay emphasis on many things regarding this control system. Since we have seen this polynomial, we also have a criterion called as the Routh-Hurwitz criterion, by which a particular polynomial is considered to be stable or unstable. The Routh-Hurwitz criterion is going to take the coefficients of the polynomial and say whether it is going to be stable or unstable. But it is going to also separate the numerator into zeros and denominator into poles, and it is going to see how many zeros and how many poles the particular control system function has, depending on the number of poles and zeros located on the complex plane, that is x and j plane. Instead of saying y plane, x and j plane, it is going to determine whether the control system is going to be stable or not. This particular analysis is done in an easy method by taking the coefficients called as the Routh-Hurwitz criterion. The following method of analysis, which is tracing the Routh-Hurwitz criterion, is going to be the Nyquist analysis. But before that, we are going to see the Routh-Hurwitz criterion. But in a simple term, if we apply the same criterion for looking into this polynomial, this is a simple polynomial for such a criterion. If you look into the polynomial, you see the polynomial now 3s plus 1 by s minus 1 into s minus 2 into s plus 1. Here we have got the poles 1, 2 and minus 1. 1, 2 will be located on the complex plane, but it is going to be located on the right hand side. The minus 1 is going to be located on the left hand side, but what about the 0? 0 is going to be a minus 1, which is going to be located on the left hand side of the plane. So if we have one of the poles or some of the zeros located on the right hand side of the complex plane, then it is going to be unstable. That's what the criterion says, and it is staying with the same statement such that the number of poles or proximity or increase in the number of poles located on the right hand side of the plane is going to add to the instability of the particular control system. So when we want to analyze the control system part by part, then we can say that the pole corresponding to that part, which is located on the right hand side of the plane, is going to create instability. So that particular portion of the control system has to be adjusted such that it is not going to create any complexity further in terms of instability. So this is one example of analysis using some condition. Such conditions and analysis are taken in the control systems for the stability. And we have seen the transfer function and also a condition for stability. To explain. Now, this particular function with S domain is not a simple function, it is going to be a complex function. When I say complex function, it is not a complicated function. Complex means it has got a real and imaginary part. So I can say that the S is going to be separated into real and imaginary part. This real and imaginary part of the S function is going to be plotted in a complex plane. Complex plane has got the xy plane with some rotation of 90 degree. So when we plot such a polynomial in the complex plane with their zeros and poles, so then we can say that it is called as a Nyquist stability plot. But there is a difference between the Nyquist plot and the other criterion, root service criterion, wherein the root service criterion is going to take the coefficients looking at the polynomial. Just now we saw the polynomials looking at the polynomial 3s plus 1 by s minus 1, s minus 2 and s plus 1. We can look into the polynomial and then see that we have poles and zeros. But in the Nyquist stability criterion, we are going to resolve this into its roots. And we are also going to see the response curves. That means this is going to be related to the next plot, which is called as the Bode plot, which is dependent on the frequency of this particular function. The frequency analysis can also be done with this particular function depending on the input signal. So this is a intermediate. The Nyquist plot is an intermediate between the root service criterion of stability and the frequency response seen in the Bode plot. It is not a fully maximal criterion to say that it is a proper control system or it is a stable control system. The Nyquist plot is just a complex point representation. It is not good to decide whether this is a control system which is going to be stable in future or it is going to give a good frequency response. So Nyquist plot to the maximum can give some overall idea about the control system in the complex plane, not the complicated plane, complex. It is a complex analysis plane. We have a stability plot associated with the Nyquist. It says that a Nyquist path is a contour in the S-plane which completely encloses the entire right half of the S-plane. So we have the S-plane. Now we are coming into the S domain, so we are going to speak not in terms of xy plane. We will say that it is going to be S-plane. The S-plane which completely encloses the entire right half of the S-plane, then the contour contributes to the Nyquist path. This particular Nyquist path is very important in determining the limit and the proximity of the poles located on such a plane, such that they contribute to the stability of the particular transfer function of the control system. This is going to be analyzed as a stable control system or not, but not in detail. Right, looking at the polynomial, but it is going to give some good analysis such that this Nyquist plot can be taken as the revaluation of the root service criterion. Root service criterion has already given us whether it is a stable system or not, but Nyquist plot is going to ascertain to us that it is going to be stable depending on the location of the poles in the RHP. So the Nyquist stability plot says check for poles on the j omega axis. J omega axis is the vertical axis, and check for the poles towards the origin. Our origin is defined for every axis, and check for poles in the j omega axis on the origin. Then it says that image path has to be plotted. Even though we have such poles, image path has to be plotted such that the other poles form an image. This is called as an image path. We connect this origin and the axis poles to other poles, and we form an image path. For example, a diffraction X-ray image or a centrifugal image. They have got such an appearance. We can compare such a plot with such an appearance. Then connect all the curves. Then recall the image of a closed contour. Closed contour image has to be recalled. This is called as a conformal mapping. Conformal mapping with an analysis saying that these particular poles are nearby, these particular poles are far away. This is called as a conformal mapping. The image in the Pierce plane of the corner angles of the semicircles in the Nyquist path have to be determined. So corner angles of the semicircles in the Nyquist path, they are going to be determined. That means the Nyquist plot cannot be called as a linear plot. They are converted into more or less a polar plot. That means our plot is connected not by straight lines, but they are connected by curves and circles. Remember, our product of inverse Laplace transform yielded us exponential curves, decaying exponential curves, and other curves. It may be a sum of exponential curves, or it may be a subtraction of exponential curves. So we are dealing with curves now. The Nyquist plot has converted the polynomial equation into one such a polar plot or a circular curve path, such that all poles are connected, or to the maximum the number of poles are connected in terms of curves, in terms of circles. So this is forming a region, this is forming a path, and this is forming a circle called as a Nyquist stability circle, within which if the pole is located, then the system is going to be stable, and if the pole is going to be located far away from the or if many poles are located far away from the stability circle, then the system is not going to be stable further. This is what we are deciding with the geometry analysis of a particular transfer function of the control system. Thank you very much for listening. We will come back again with the control system concepts.